here at Cybotz.
I'm Harshit.
I'm Rishi Kandala. I'm at team 5795, and me and Chin are two co-mech leads. And this is my second year in FTC, and this is his third year in FTC.
Hi everyone, hope you had an amazing morning. I'm Achinta Huja. Like Rishi said, this is my third year in FTC, but I've been in first overall for 6 years. And welcome to our presentation about 3D printing and manufacturing. So to start, our presentation is to cover 3D printing basics, so what 3D printing is, how to purchase a 3D printer, because you know that guide can be kind of difficult, and it also covers different price ranges, the different types of 3D printing filaments, and how to develop custom parts with the to actually get the 3D printer to print them.
We'll also cover how to optimize part orientation so that your print doesn't actually fail and that your print comes in the best quality. We'll also show you guys how to slicer actual things from CAD so that it's ready to print, and then we'll show you how to use heat set inserts on your 3D prints along with CNC basics, which we'll go into later.
All right, let's begin by discussing what 3D printing actually is. 3D printing is a technology where we sequentially deposit plastic in a three-dimensional manner to create physical objects. But first, let's talk about our team. Cybotz is a fourth-year team. We have a 95% 3D printed robot, as you can see over here. We have a lot of experience in 3D printed. We've donated a 3D printer, and we also build our own 3D printers too, as you can see on the right.
And we are team 5795. We are a veteran team from 2013. We are part of a bigger organization called FTC Robotics. You might see a couple of people over here that are also from FTC Robotics. We are from Greensboro. We also have a fully custom robot, which isn't here right now, but we have parts of it to show you guys. And you can see right here, this is a render. This is our team from last year. A lot of them were seniors, so they left, so you might not know them. If you see the blue hats, that's us. Right back there in the very back, that's us. We're 5795, so you will be seeing us a lot around today.
So imagine 3D printing being like a motorized hot glue gun that can move in all three dimensions. As you can see on the left, it takes time. It's a three-dimensional process. Every layer of plastic is extruded on top of each other. You can see in this picture over here, the individual layers that a 3D print is created out of. There's 4 parts to a 3D printer: the tubing, the extruder, the hot end, and the nozzle. The material that we use in 3D printing is called filament. Harsha, can you show us the rule of filament? This is what's extruded through the hot glue gun per se to create the material.
All right, so how to purchase a 3D printer. So 3D printers come in really big ranges. These are some of the examples that we've got for you, but there's a huge budget range. It can go from like $199, like $200, all the way up to like $3,000, $4,000 ones. And we're gonna just show you the pros and cons of these 3D printers and why some of them might be good, some of them might not be good for you. So the A1, Bamboo, these are all Bamboo Lab printers, and Bamboo Lab is the reason we picked Bamboo Lab is because it's the most reliable, best quality, and they're really fast as well. So Bamboo Lab A1, this is really good if you want to do printers, print at home, and it's nice and small, petite, and it also has a camera, so if you are like not at home, you can also look at your prints, and you can also change out your filaments like you can see right here. And then there's also the P1P. P1P is bigger. It has an actual enclosure, which is really good if you want to do filaments like ABS, which need enclosures to actually print. And it also has auto bed leveling, and so does the A1, which means that you don't have to level the bed by yourself manually, and it's a really good feature on these printers.
And so finally, the last printer is the X1C or X1 Carbon. This printer is more industry grade, as it has a fully enclosed heat-in structure, which allows you to print ABS and other filaments like nylon extremely easily. It also reduces the noise and makes the printing environment even safer. Just like the other printers, it has a camera, but the big thing about this one is it has a failure detection, which means that if the print fails, as soon as the print fails, the Bamboo Lab will stop printing overall, and you can save time. You can save your filament.
All right, now let's talk about the 2 most common types of filament used in FTC. The first filament is called PLA, stands for polylactic acid. It's derived from cornstarch and has a really low melting point. It's extremely easy to print. However, there's another material called PETG. It stands for polyethylene tetraphthalate glycol. This black roll right here is PLA, and this roll here is PETG. Can you show me the samples? A PLA has a higher tensile strength, but it's brittle, so it'll snap before PETG. So if I bend this, hold this one. If I bend this black piece of PLA, it'll snap like this. However, I do it with PTG, it'll just bend because PTG is a lot more softer and will bend before it breaks. So you want to keep that in mind when deciding what plastic to use. PTG also tends to string a lot, as you can see in this image. So you want to make sure you dry your PTG filament before you use it.
Yeah, so a couple other more unorthodox filaments are carbon fiber, TPU, and nylon. So carbon fiber, what's really great about carbon fiber is that it's a lot more durable and durable than PETG and PLA. Carbon fiber comes in like three main types. We have fully carbon fiber filament, which is kind of rare, especially because most printers can't actually print fully carbon fiber because it's so brittle. And then you also have carbon fiber infused PETG and carbon fiber infused PLA, which is the two filaments that you saw before. What carbon fiber infused does is it basically it's like 2% or 3% carbon fiber into the filament, and it makes it just stronger and more rigid. So let's just say you're making a claw, and it's something that you don't want to break. Carbon fiber can be an option that you want to choose because it makes it stronger and it's more durable on the feel, and you're not going to have it snapping for pieces. Doesn't mean it's not going to snap, but it's just a lot stronger. Couple issues with this though is that it's a lot harder to print, and you want to have an enclosed printer, but like carbon fiber, sorry, like the X1C or the P1P, because you don't want the carbon fiber to fumes and stuff to get around your room, and it's cancerous, obviously. So you want to have an enclosed printer for that, and it also has a lot smaller of a print temperature settings. So you want to make sure you have good settings for it so it does not fail.
And then the other type of filament we're talking about is thermoplastic polyurethane, or TPU. This filament needs a higher printing temperature than PLA because it's really flexible. So that means in real life, it's used for phone straps and cases. But in FTC, we can use it for belts. It's the big part about TPU is that it's flexible and elastic, which means it's harder to print as well. Because it's so flexible, the supports, it's more difficult to print supports, and you need to print at a slower speed, so it takes much longer than PLA or PETG. And then nylon is another like more unorthodox filament. It prints at a similar temperature to TPU, but it's also best used for mechanical prototypes. And this is because it's more flexible than PLA, PETG, and carbon fiber filaments, but it's less flexible than TPU. And because of this, it's also very durable because of its flexibility. For this, it's recommended to print it with a heat embedded enclosure, which makes it difficult. That's a big con of it because you need a specific type of printer like the X1 Carbon. And another thing is it absorbs moisture really easily. So if you don't want to leave it out in a humid environment.
Since you guys use CPUs and robots, and things like flexible and bendable.
You can also use TPU to make belts, which is sometimes people don't recommend it, but it is something that some robotics teams have tried. So if you guys are willing to do that, you might get it.
Okay, let's talk about the custom part design process. The first thing you want to do when you want to create a part is first determine whether or not you actually need to create a custom part. It's not worth your time to design, 3D print, and iterate something when you could just use an off-the-shelf metal part that you'd buy off GoBuilda. So once you've concluded that you need to make a custom part, you want to first analyze the problem, see what kind of design constraints you have. Then you want to define the requirements. What does this part need to do? Where does it need to fit? How much weight does it need to hold? Then you want to use CAD to design the part, and then you can iterate it, making improvements to each design and keep printing it over and over again.
All right, so we're just gonna go delve a bit deeper. So we're gonna take the example of a battery mount. You have your battery mount?
Okay.
So we're gonna take an example of a battery mount. So let's just say you need something to hold your battery on your body. So what are you gonna do first? You want to find your problem. Problem in this case is you don't have a place to that can securely hold your battery, right? So that's your problem. Great job. You're done with step one. Step two, you want to find the requirements. You want to know the actual measurements and where your holes are. So how am I going to mount it? It's not just going to float in the middle of the bot, right? You want to find where you want to put your holes, how it's going to actually be on the bot, and then how big it's going to be. You want to make sure you have tolerances because you don't want your battery to be like fit inside there because 3D prints also expand, which means your tolerance should be at least like 0.5 millimeters, so that it actually fits in there. Once you're done with that, we recommend that you actually sketch out what you want to do before you start CADing, because sketches are a great way for you to start envisioning what you want to put out on the CAD, because CAD is a really long process, and you don't want to CAD something and then realize, oh, maybe that might not work.
Okay, so like Richie said, after your sketch, you can take this design into CAD or computer-aided design. This pretty much means that so the process of CAD starts with simple sketches and extrudes. So say I'm going to go with a battery holder again. I would start with a simple rectangle, and I would extrude that up. So I would make it a 3D object, and then I would shell out the insides and fillet the edges or curve the edges. And once this is all done, you can also, one thing we recommend is something called pocketing, or creating these small holes right here. As you can see the honeycomb design right there. And this is because it reduces the weight of the object by a lot, and this is really important at FTC because you want to have a lightweight robot. And something about the honeycomb design, because it gets rid of a lot of material, but it also is still strong, and it's really efficient because of the material lost.
All right, now let's talk about optimizing print orientation. Believe it or not, the way you orient your 3D print on the build plate as you print it has an extremely key role in how strong the part is. 3D prints are built in layers, meaning they're only strong in one direction. The way you apply the load, as you can see in this top image here, determines how strong the part will be. If you apply the load incorrectly against the layer lines, the part will break along the layer lines. We also need to keep in mind how we orient the part to minimize the amount of support material needed. On this image here on the left, this part here is the exact same part, oriented in 3 different ways. If you have it oriented like this or this, you will need to waste a lot of material and time with supports. However, if you simply orient it like this, no supports will be needed at all, greatly saving time. You also want to keep this in mind when designing your parts. On the leftmost image here, there's an overhang. That one is not chamfered. That will require supports to print, but simply chamfering that and making it a 45-degree overhang will make it 3D printable without supports. All right, now let's talk about slicing. So what is slicing? Slicing is a technology used to turn a physical CAD model on your computer and slicing it into the individual layers that the machine reads as the code to create the object. As you can see in this diagram here, we start with the STL file that you import directly out of Onshape or whatever CAD software into the slicer. The slicer software then chops up that individual parts into hundreds of layers and converts it into a file format known as G-code. The G-code is the individual X, Y, and Z code that the machine can read and understand as to where to put the plastic. And that's what the 3D printer reads. Now, in the slicer, there's several settings that you can pick and select to determine how the part turns out. We'll go into more depth on the next slide, but they're the walls, the bottom, the infill, and the infill density. All right, let's talk about the key slicer settings. So probably one of the most important ones is the infill pattern and density. A 3D print is not fully solid. Inside, there's air. So based on how much infill you want, the infill is the amount of plastic that's inside the part. 10% means that there's 10% of plastic inside the part. 25% means there's 25% of plastic inside the part. And 50, as you can see on the way all the way on the left, means there's even more plastic. So obviously, the more plastic you add inside the part, the stronger it will be, but also increase the weight. There's also a lot of patterns to the infill you can see. Our favorite infill at Cybotz is gyroid. It's one of the fastest, and it's good for strength when the load is being applied in multiple directions. The other thing is the walls. The walls is the amount of plastic that go around the boundaries, the perimeter of the part. So it's similar to infill. As you add more walls, the stronger it will be, but also increase weight. All right, now let's talk about slicing. So on the top bar over there, you can see 4 different slicers. It's Bamboo. The one highlighted in red is Bamboo Studio. That's the one we recommend. It is what's used with all Bamboo Lab printers. We have Orca Slicer, Prusa Slicer, and Cura, which are also very common for many 3D printers. However, the process for using a slicer in almost all softwares is virtually the same. You want to begin by first importing the part out of CAD into the slicer. Then you want to change the settings as we discussed in the previous slide. Then you want to slice the plate to generate toolpaths in G-code. And then you want to visualize the preview. The preview is a tool that all slicers have. It allows you to see exactly what the 3D printer will produce. So you can catch various errors that you would not want to see after the part's printed, like if you put supports in an area that you don't want to. So we always recommend that you check the preview before you send the print. All right, support types. So supports are used to support overhangs. 3D printers cannot print against gravity. When it puts plastic above air, it will droop down. So you need something to support it. There's two types of support. There's normal, which kind of look like towers, and then there's tree support, which sort of look like tree branches. So normal supports, they have several advantages. They're easier to generate and they're stable. However, they use more filament and they leave marks underneath the bottom of the 3D print. Tree supports, on the other hand, they use a lot less material, they're easier to remove, and they leave less minimal marks underneath the area they support. However, they can fail on complex parts, so it's important to use them carefully. All right, heatset inserts. Heatset inserts are something that we use a lot at Cybotz and would like to share with the rest of the FTC community. They're little brass threaded inserts. So they're threads inside this thing and allow screws to be put in. So you heat them up and you press them into a hole using a soldering iron. So all the panels on this robot are attached using heatset inserts, and it allows us to take parts off 3D prints and put them back on without stripping the hole that they're attached to. So you want to be careful with them when you're installing them, as you can get burnt really easily. But they're a really powerful tool that we'd like to see being used a lot more.
All right, so we're going to take a step away from 3D printing since this is also a manufacturing class. We're going to talk about CNC machining. So we are fortunate as DC Robotics. We have 4 different FTC teams and an FRC team. So we have an in-house CNC. So we have, over the years, become very accustomed and we've learned a lot about CNC machining and the best ways to do it. So what is CNC machining? It's actually, CNC stands for computer numerical control. And what that just really means is the actual system that's controlling the machine, and that's a CNC. CNCs come in different forms, but what we use in FTC is CNC milling. Milling is nothing but cutting. It's typical to cut 2D and 3D parts. In robotics, we usually make stuff like side plates. You have a big sheet and then you cut it out with the machine, and you can make holes and stuff like that. So side plates, you can also see that a lot of our intake this past year was CNC. So all the aluminum parts were CNC, including this little linkage, which pushed this down. The great thing about CNC and its benefits over 3D printing is that you can cut metal with it, and metal is obviously a lot more durable and won't shatter like 3D prints. So if you have something that you seriously do not want to break, then CNCing can always be your option. Issues with CNC, sometimes it takes a really long time to actually manufacture, and they have its limits as well, and it's not as versatile as 3D prints.
So like Rishi said, CNCs are used commonly in robotics, and one of the big things they're used for is side plates. So you can see right here, we cut this last year for our first design, and this is used to support the rest of the robot. And we can also use it for spacers and mounts, which we don't have right now. But the big thing is they can allow cutouts. So if you see on this one, we had these like little pockets right here, and we pass our wires through these little pockets so that we can to make our wiring much neater and easier. And also they can be used to show your team personality. So like on this side plate right here, we wrote 5795 across to show that to show our team number and the honeycomb design show our team like spirit.
All right, the CNC workflow. So like 3D printing, this also has a couple steps that you got to take, and it's generally accepted across the FTC community. The first, obviously, you want to design your actual product. So after you design it and you take the STO file, just like 3D printing, you put in a different software, not slicing, but you're going to do something called CAM. CAM stands for Computer Aided Manufacturing. So all it's doing is basically doing what 3D printing does, but for a CNC machine. And it does something called toolpaths. So if you can see right here, these yellow lines is what the CNC machine is what it plans to actually cut. So you make your toolpaths and you set its settings, so how fast you want it to go, how fast the spindle is going to turn, and stuff like that. So it goes around, and then you want to make sure that you do a simulation. You want to watch it do its cut, just like the preview of a slicer. All right, and once you're ready to go, you export it and you actually cut it. Just like a 3D printer, it reads a cheat code, and it's just a movement, where it needs to go, and stuff like that. And that's the basics of CNC workflow. And yeah.
So the big benefits of using a CNC and camming in FTC is that you get to choose your own speeds, and you get to choose your own like part you want to do. So with camming, you can choose like this, like Rishi said, you can choose different types. So if you want to use the type of end mill you use, if you use a larger diameter end mill, the cut will go a lot faster, but it might be less accurate. And if you use a smaller end mill, it'd be more accurate, but it goes slower. And same thing with the spindle speeds. If you go faster, the cut's gonna take less time, but the cut might not finish as good as it would be if it take it slower. Additionally, CNCs they're really accurate. So if you want to cut a part multiple times, like we did right here, so you wanted to cut 2 identical side plates. So if we were to cut these side plates 2 times, they would be identical, which is a really important part, and that's a similar thing with 3D printing. And also, like we said earlier, it allows us to like show our own personality and style. But one thing to be worried, like to notice about when you're CNCing, is that you need to make sure your cam is done properly. Like I said earlier, if you choose the wrong spindle speed, like you go too fast on the wrong material and use the wrong type of bit, it may lead to your the end mill breaking, and it costs a lot of money. And then, like Rishi said, you should always simulate your tool paths just like in 3D printing, because say it cuts in the wrong direction or cuts in the wrong order. So say you cut the outside of the plate before the inside, the plate can fly off. And this is also a big thing. You need to be safe when you're cutting. So wear safety glasses. Make sure you're printing with an enclosure, cutting with an enclosure on as well.
CNCs are a lot bigger, more expensive, and a lot more dangerous. So you want to take a lot more precautions when you're cutting with a CNC machine. That brings us to our end of our presentation. We hope you liked it. If you have any questions, this is the time.